An electronic circuit which converts pure AC into pulsating DC, or a circuit which converts bidirectional waveform into unidirectional waveform is called rectifiers. So, rectifier converts pure AC into pulsating DC. So, what is pure AC? Properties of pure AC. The waveform here I am showing is pure AC waveform. So by looking into this waveform, I can say this waveform has periodic variation. That means this waveform is a periodic signal. Periodic signal means the signal is repeating itself at a regular interval of time. So consider this waveform here. I am writing this one is pi. Okay, this angle is pi and this angle is 2 pi and this angle is 3 pi. Okay, so the signal is repeating itself at a regular interval of time. This regular interval of time is known as fundamental time period indicated by t. Okay, the repeating time interval is known as fundamental time period indicated by capital letter T. In this figure, after 2 pi width, after 2 pi angle, the signal is repeating. Okay, then this one is 4 pi. Okay, after a 2 pi width, the signal is repeating from the interval 2 pi to 4 pi. Then again, at 4 pi onwards, the signal is repeating. 4 pi to 6 pi, the signal is repeating. Then from 6 pi to 8 pi, the signal is repeating. So the fundamental time period, the time interval at which signal is repeating itself, in this example is 2 pi. Okay, so this is known as periodic signal. A periodic signal is the signal which is repeating itself at a fixed interval of time. A periodic signal is a signal which is repeating at a regular interval of time. In this example, the fundamental time period t is given by 2 pi. That means at every 2 pi width, the signal is repeating. Okay, so this one is the first property of pure AC signal. And the next one is bidirectional. The bidirectional means the waveform have both negative values and positive values. So in this figure, the waveform has negative values, or negative half cycle is there, as well as positive half cycle is there. So the waveform has both negative and positive values. Then we can say that waveform is bidirectional one. So in the figure I can understood that this one is a bidirectional waveform. Then the third property is zero average value or zero DC value. That means zero average value, I can say it is a zero DC value. That means this waveform has zero DC value. That means if I am taking the area of this waveform over a full time period, that means over a full fundamental time period, that is 2 pi. If I am taking area of the signal over the angle of 2 pi, here I am drawing the diagram one more time, then I will explain. Okay, so this is the waveform shown. So this width is 2 pi and this width is 2 pi. Okay, then how to find out? Here I am trying to say that how to find out the average value of a signal. So the average value can be found out by taking the area of the signal over the full time period or over the fundamental time period. Here the fundamental time period of the signal is 2 pi. So I am taking area of in the 2 pi width, that means in the 0 to 2 pi time interval, two half cycles are included. So one is one positive half cycle and one negative half cycle. So I am going to take area of this one positive half cycle and one negative half cycle. So by looking onto this diagram, I can say that the area of the positive half cycle is same as area of the negative half cycle. Both are in opposite polarity, both are in different side. So I can say the area is 0. The area under this waveform over the time period of 2 pi is 0. That is why I am saying that the signal has 0 average value or 0 DC value. So average value can be found out by area of the signal. Take the area of the signal over the fundamental time period. Okay, area is same as integration. So I can say, I can modify the statement. The average value of a signal can be found out by integrate the signal over the full time period or over the fundamental time period. Okay, so here I am integrating the signal at the width of 0 to 2 pi, from 0 to 2 pi. If I am integrating the signal and the limit is 0 to 2 pi, I will get the answer as 0. So I can say the signal, the given waveform has 0 average value or 0 DC value. And the next property of pure AC signal is it has only one frequency. Okay, that is no harmonics is present. So in this example, I can say this waveform has a frequency of f0. Okay, this waveform, a pure AC signal, has only one frequency. No harmonics is present. Harmonics means one fundamental frequency is there, then integer multiples of fundamental frequency is known as harmonics. So in this example, in this figure, this waveform has fundamental frequency of f0. So the 2f0, 3f0, 4f0, 5f0, 6f0 and so on. These are called harmonics. So a pure AC signal doesn't have harmonics, it has only fundamental frequency. So then how to find out the fundamental frequency of a signal, or how to verify that the signal contains only the one frequency, no harmonics? To find out the frequency components present in the waveform, we can use the Fourier analysis. We can use Fourier analysis. I am not going to explain the Fourier analysis, but remember that to find out the frequency components of a signal, we can use Fourier analysis. Fourier series is there, Fourier transform also there. So to find out what are the frequency component present in a given signal, we can use Fourier analysis. So the property of pure AC is it has only one frequency. That means there is no harmonics present. It has only one frequency, that is fundamental frequency. So these are the properties of pure AC signal. So the rectifier converts pure AC into pulsating DC. Next we are going to see what are the properties of pulsating DC. Okay. So these are the properties of pulsating DC. Pulsating DC, the first property is it has periodic variation. That means here I am showing the two examples of pulsating DC. Then by looking into these two diagrams, I can say a periodic variation. That means signal is repeating from the first, looking onto the first diagram, figure 1, the signal is repeating itself at a regular interval of time. What is that regular interval of time, or what is the fundamental time period? Fundamental time period is pi. After the width of pi, the signal is repeating. Then coming to the next diagram, figure 2. In the figure also, in this figure also, the fundamental time period is pi. That means the signal is repeating at a regular interval of time. Here the regular interval of time is termed as fundamental time period. In this figure, the fundamental time period is pi. That means at every pi, the signal is repeating. Okay, so this is the first property of pulsating DC. It has periodic variation. And the second one is it is unidirectional. That means varies either positive or negative direction. So look onto this diagram. The first diagram, the signal have only positive value. The second diagram, the signal has only the negative value. That means the pulsating DC has either negative values or positive values. And the third property is it has non-zero average value or the non-zero DC value. So remember, I have already told that how to find out the average value. We can integrate or take the area of the signal over the full time period. So in this example, the fundamental time period is pi. So to find out the average value or DC value, take the area of this waveform over the time period of pi. So that means this is the area. Okay. In the second figure, this is the area. Or we can integrate the signal, and the limit is 0 to pi. Okay. So definitely we can say that it is not a zero value. It is a non-zero value. The area or the result of integration is a non-zero value. So I can say the pulsating DC has a non-zero average value. The area is a non-zero value. That means the signal has DC value. So the pulsating DC has non-zero average value or the non-zero DC value. And the next property of pulsating DC is it has harmonics. That means it contains fundamental frequency as well as or multiples of fundamental frequency. The multiples of fundamental frequency is known as harmonics. It has many frequency components such that f0, 2f0, 3f0, 4f0, so on. So it has fundamental frequency and also the multiples of fundamental frequency. Then again look on to this diagram with the waveform of pulsating DC. I have already stated that it has the periodic variation. So the periodic variation indicates that the presence of AC component or the time varying component. The periodic variation indicates that the waveform contains AC component or the time varying component. The next point is the non-zero average. Already given that the properties of pulsating DC, it has non-zero average value. So the non-zero average value indicates that the pulsating DC has the presence of DC component. So there are two conclusions from these two statements: periodic variation and non-zero average value. The periodic variation indicates that presence of AC component, and the non-zero average value indicates that the presence of DC component. Okay, so hence I can say the pulsating DC is a combination of AC and DC components. The periodic variation, the first property of pulsating DC is periodic variation. The periodic variation indicates that presence of AC component. Then the next property of pulsating DC is it has non-zero DC value. It indicates that it indicates the presence of DC component. So combining these two points, I can say the pulsating DC contains, or pulsating DC is a combination of both AC and DC components. Next is what is a regulated power supply. In the top I am drawing two waveform fluctuating DC and stable DC, that I will explain later. Next we are moving to a regulated power supply. The regulated power supply is an interconnection of rectifiers, filters and voltage regulator. Okay, in this today's session we are going to discuss about only the rectifiers, but the regulated power supply is an interconnection of rectifiers, filters and voltage regulator. Okay, already I have stated that the rectifier which converts pure AC into pulsating DC. So the input to the rectifier is a pure AC. Already I have drawn the waveform of a pure AC signal. Okay, look onto this one. It has periodic variation, bidirectional, zero average value, and contains only one frequency. Then rectifier converts pulsating DC. It is a combination of AC and DC. Then this waveform, this pulsating DC, is given to the filter. The filter, for the example for filters are capacitor filter, induction filter, pi filter, etc. The filter converts fluctuating DC. The output of filter is a fluctuating DC. Filter converts pulsating DC into fluctuating DC. So the input to the filter is pulsating DC. The output is fluctuating DC. Okay, then the waveform of fluctuating DC is shown in the top. So the fluctuating DC also a variation system. When you observe this waveform, you can see that variations in the waveform. This is not a constant value. A small variations are there in the waveform. Okay, so we want to get the DC waveform. DC waveform means what? It always providing a constant value throughout the time. For example, when you consider the battery, AA battery or AAA battery, there it is written 1.5 volt or 2 volt, etc. So what do you mean by that 1.5 volt DC? 1.5 volt DC means it provides constant value of voltage. That means here 1.5 volt, it provides 1.5 volt voltage throughout the time. That means minus infinity to positive infinity. Okay, the whole time it provides the constant value of magnitude 1.5. That means DC. I can say stable DC. Okay, stable DC. So what is the use? What is the use of this stable DC? All the electronic components are for the proper working of all the electronic components. We want to given the supply, and the supply is in the form of DC. For example, laptop, mobile phone, and everything. We need the DC signal. Okay, the supply from our electric lines. For in India, the supply from our electrical line is AC, and it is 220 volt, 220 volt RMS value and 50 hertz signal. 220 volt RMS value and 50 hertz signal. So in order to operate all these electronic components, we need DC power. So to get the DC power from the AC, we are using the regulated power supply. Rectifier is one of the component in the regulated power supply. So the output of the filter is fluctuating DC. Actually, the output of the filter is not an stable DC. It has variation. So to get the stable DC, or to eliminate the fluctuations in the output of the filter, next, the third stage, we are using the voltage regulator. Voltage regulator converts the fluctuating DC into stable DC. The stable DC signal is also known as a regulated DC signal. So this is the simple block diagram of a regulated power supply. The next topic, we are going to see classification of rectifiers. Rectifiers can be classified into two types: half wave rectifier and full wave rectifier. The full wave rectifier is again classified into two: center tapped full wave rectifier and bridge full wave rectifier. Okay, in this slide I am showing the waveform or the circuit diagram of a half wave rectifier. So half wave rectifier contains only one diode. Half wave rectifier contains only one diode. Contains only one diode. And the diode, and the main feature or main point in the half wave rectifier is this diode conducts in only one half cycle. Only one half cycle of the input voltage. Okay, so in the next slide I will show the input waveform. So here I am showing the first I will in the first session I will written, it is written the pure AC signal. Actually this one here I am showing this one. In circle I am showing in circles I am showing that is a transformer. It is a step down transformer, because the pure AC, that means the signal, the supply voltage from our electrical lines, the KSEB electrical lines. Here the supply voltage, it is, the specification is 220 volt RMS value. RMS means root mean square value, RMS value, and the frequency is 50 hertz. Okay, then you all of you know that all the electronic components need DC, and these all electronic components are working in the range working in the range of 10 volt or 5 volt, 12 volt, etc. These all are low power devices. So in the lines, from the electric lines, it is 220 volt RMS value. So first we have to step down this value, this voltage, into a smaller one. Okay, so the for this purpose we are using a step down transformer. So the step down transformer reduce the input voltage. Okay, so that it reduce the 220 volt RMS voltage to a low value, low voltage. So I can say this waveform or this circuit, half wave rectifier, is an example of low voltage rectifier, because here I am using a step down transformer to reduce the input voltage. So this is the circuit diagram shown here is an example for low voltage rectifier. Okay, because it uses the step down transformer to reduce the strength of AC voltage. Okay, so this is the purpose of step down transformer. Then what is the in the input to the step down transformer we are applying pure AC signal 220 volt RMS 50 Hz. Then at the secondary side, the output of the transformer is also an AC signal. Okay, that is indicated by VI. The output of the step down transformer is also an AC signal indicated by VI. Okay, this VI is given to the diode. The VI is given to the diode D. Okay, then the waveform of VI, just I am drawing here. The waveform of VI is just I am drawing here. It's also a AC signal. Okay, so it has two half cycles. One is positive half cycle and one is negative half cycle. This I can write, this one is pi and this is 2 pi. Okay, the fundamental time period is 2 pi. Fundamental time period is 2 pi. So the positive half cycle is from positive half cycle from 0 to omega t from 0 to pi. The negative half cycle from pi to 2 pi. Got it? Okay, so the output of the secondary transformer or the voltage at the secondary winding is also a AC signal which is given to the or which is applied to the diode. Okay, then here I have written one statement: diode conducts in only one half cycle of the input voltage. That means the diode in the half wave rectifier, diode is conducting only either in 0 to pi or in pi to 2 pi. I will explain in this diagram in which half cycle diode is conducting. Okay, before going to that, let me explain one more notations. So I can write VI. Already I have stated that VI is an AC signal. Okay, the common method or the usual procedure to represent an AC signal is in the form of sinusoidal. Always or commonly we are representing AC signal. Mathematically we are representing AC signal as a function of sinusoidal signal. Sinusoidal means sine, cosine signal. So here I am writing VI is the AC signal. Here I am writing Vm sine omega t. Okay, VA mathematically the input to the diode is represented by Vm sin omega t. It is the usual practice. Always we are representing AC signal as a function of sinusoidal signals. Then this Vm is known as, this is Vm. Okay, this is Vm. That is, this point is Vm, maximum value at the positive half cycle. In negative half cycle, this is also a Vm, but polarity is different. This is minus Vm. So Vm is known as maximum value or peak value. It is known as peak value voltage or maximum value of voltage. Then what is the RMS value of this waveform? Okay, any AC signal is represented by, or any AC signal is characterized by two points. One is RMS value. Any AC signal, specifications of AC signal, an AC signal is represented in terms, or what are the identities of an AC signal. One is RMS value and the next one is frequency. These are the two identities of a AC signal. So RMS value. So I have already stated that Vi is an AC signal. So what is the RMS value? RMS value of this signal, it is a sinusoidal signal. The RMS value of a sinusoidal signal is Vm divided by root 2. Okay, this is RMS value. Root means square value. Okay, RMS value of an AC signal. This is a AC signal and it has, the waveform looks like sinusoidal. Okay, the RMS value of any sinusoidal signal is Vm divided by root 2, where Vm is the peak value or maximum value. The next parameter is omega. Omega is known as angular frequency. Omega is known as angular frequency. Angular frequency, and the unit of angular frequency is radian per second, and omega is equal to 2 pi f. Omega is equal to 2 pi f, and the fundamental time period t is equal to 1 by f. These are the some basic expressions. Then I have already told that in India it's a 220 volt is the supply voltage, or the voltage from the line, electric lines. So the 220 volts is known as line voltage. 220 volt is known as line voltage, and the 50 hertz is known as line frequency. In India, the frequency of the supply voltage is 50 hertz. It may be vary in outside, in USA or Europe. It has a different frequency. 60 hertz is there, but in India the line frequency is 50 hertz. Okay, then Vi is a pure AC signal having the smaller RMS value. So the line frequency is 50 hertz. That means f is 50 hertz. So I can find out the angular frequency. Angular frequency is equal to 2 pi f, which is equal to 2 pi into 50, which is equal to 100 pi. Pi means 3.14. 3.14 into 100 means 314. So the angular frequency is 314 radian per second. Okay, these are the some basic equations related to the AC waveform. Okay, now I am going to our topic, half-wave rectifier. Okay, already told that the half-wave rectifier diodes conduct in only one half cycle of the input voltage. So here the input voltage Vi is shown here. So diode can be conduct either 0 to pi half cycle or pi to 2 pi half cycle. So now we are going to check this diode. In the given diagram, this diode is going to conduct in which half cycle, negative or positive, that we have to determine. So first I am checking the first half cycle, positive half cycle, omega t from 0 to pi. Then in this diagram, the 0 to 2 pi means it is a positive half cycle. It is a positive half cycle. In positive half cycle, Vi is positive voltage. So I can say Vi is positive voltage. Okay, the same diagram I am drawing in this slide also. Vi is shown here. The fundamental time period is 2 pi. Now we are considering the first half cycle. That means 0 to 2 pi. First half cycle 0 to pi. In 0 to pi, the supply voltage Vi or the input voltage to the diode Vi is positive. Okay, then all of you know that the diode is operating in two modes. Diode is operating in two modes. First mode of operation is forward bias and the second mode of operation is reverse bias. Diode has two modes of operation. First one is forward bias and the second one is reverse bias. Okay, in the diode, this is p-type semiconductor, p side, and this is n side. Okay, then when the diode becomes forward biased mode, in forward bias means when I am applying a higher voltage at p side than the voltage at the n side, then I can say diode is operating in forward bias. For example, in forward bias, I am applying a voltage of 5 volt to the p side of the diode, and I am applying 2 volt to the n side. So here the voltage at the p side is greater than that of n side. That is 2 volt is greater than 2 volt is less than 5 volt. The voltage at the p side is greater than that of n side. So I can say that the diode is in forward bias. Okay, then forward bias, or I can say diode is in conduction mode. Diode is in conduction mode. Diode is in forward bias. Same statement I can say that diode is in conduction. Conduction means a current is flowing through the diode. That means when a diode is said to be forward bias, implies that a current is flowing through the diode. Okay, the next one is reverse bias. Reverse bias means voltage at n side, or I can say voltage at the negative side. Voltage at the negative side is greater than that of p side. For example, again I am drawing the same diode. I am applying 5 voltage to the n side and 2 voltage at the p side. So here voltage at the n side is greater than that of p side. So here diode is in reverse bias mode. Reverse bias means it is a non-conducting mode. That means there is no current is flowing through the diode at the reverse bias mode. Okay, so in a reverse bias mode, I can replace this diode as a open circuit. That means there is no connection. So there is no current is flowing through this diode. In forward bias, I can say when the diode is in forward bias, a current is flowing. That means I can replace this diode as a short circuit. That means a simple wire. I can replace this circuit, or I can replace this diode as a short circuit. Okay, so coming to this half cycle 0 to pi. In 0 to pi, Vi is positive. In 0 to pi, Vi is positive. Again I am going to the previous slides. Okay, in previous slide, look onto this, the waveform of half wave rectifier. Here I am applying Vi to the p side of the diode. Okay, observe this diagram, circuit diagram. I am applying the pure AC signal voltage Vi to the p side of the waveform, and at the n side I am connecting a resistor RL, and after that it is grounded. Okay, so at the first half cycle 0 to pi, Vi is positive. That means I am applying a higher voltage at the p side than that of n side. So I can say diode is in forward bias. Okay, forward bias means diode is in conduction mode and a current is starts flowing through this diode. Okay, so the secondary winding diagram. Here I am drawing only the secondary winding diagram, secondary side. Here I am drawing only the secondary side, second part of the half wave rectifier. So here this input voltage is Vi, then diode is in forward bias. So I have already told that when the diode is forward bias, current starts flowing. Then simply I can simply I can replace this diode as a short circuit. That means it is equivalent as a wire. Indicates that current is flowing freely. Okay, so I am replacing diode as a short circuit because here diode is forward bias. Then the remaining thing, load resistor RL. Okay, so when the first half cycle diode is in forward bias, diode starts conducting. That means a current flowing through the diode. Diode is in forward bias, so I am replacing diode as a short circuit. So the waveform is shown here. So a current is flowing. A current is flowing through the diode. Okay, that current, that current I create a voltage drop across the load resistor. Okay, load resistor. A voltage is created across the load resistor. Then what is the shape of this input voltage Vi? The shape of the input voltage Vi is a sinusoidal waveform. Vi, the shape of the Vi when the range 0 to pi. What is the shape of Vi in 0 to pi range? 0 to pi range. This is the shape. Fine. This is the shape. So the current has also the same shape, and the current I has also the same shape. This current I creates voltage drop V naught across the load resistor. So the V naught has also the same shape as the input voltage Vi. So the output voltage has also a sinusoidal shape. That is why the waveform, look onto this waveform V naught. I am drawing the shape of the output voltage when the range 0 to pi. That range, the shape of the output waveform is also a sinusoidal signal. Okay, fine. Hope that you got the point. Then the second half cycle. Second half cycle means omega pi lies from pi to 2 pi. In pi to 2 pi, look onto the first diagram, Vi. Pi to 2 pi, Vi is a negative value. Vi is a negative value. That means I am applying negative voltage to the P side. So diode is in reverse bias. So when the diode is in reverse bias, I can replace this diode as a open circuit. So simply I can replace this diode as an open circuit. Then this is load resistor. That means in reverse bias mode, there is no current. There is no current is flowing through the diode. Okay, that statement I am mathematically, or sorry, I am represented as a open circuit. Okay, so when the diode is in reverse bias, there is no current is flowing through the diode. So that statement I am represented in a figure as a open circuit. So this is RL. So here diode is in reverse bias, that is non-conduction mode. No current is flowing, that is I equal to 0. Okay, there is no current is flowing, so there is no voltage. Nothing is developed across the load resistor RL. That means there is no voltage is developed across the load resistor RL. So I can say V naught is 0 because there is no current is flowing through the load resistor RL. So I can say the voltage drop across the load resistor RL equal to 0. That's why in the second half cycle, pi to 2 pi, I am drawing a red color, a horizontal line only, because there is no voltage drop, zero line voltage. I am drawing a zero line voltage in the range 0 pi to 2 pi because there is no voltage drop developed across the load resistor, that is V naught, when the omega t in the range pi to 2 pi. Okay, so this is the working of half wave rectifier. So I am summarizing the working of half wave rectifier. The half wave rectifier contains only one diode, and this diode conducts only in one half cycle of the input voltage. So in this diagram, here I am showing the supply voltage. Supply voltage has two half cycle, one is positive and one is negative. And the positive half cycle, the diode is in forward bias. That means a current is flowing through the diode. and the negative half cycle diode is in reverse bias. That means there is no current is flowing through the diode, so zero output voltage. So the output of the half wave rectifier looks like this one. So only the output voltage has value only in the range 0 to pi, and a zero value from the range pi to 2 pi, and this cycle is repeating. Okay, this is the output waveform of half wave rectifier.